In this section, we're going to take a look at the idea of this directional derivative, and then we're also going to take a look at this thing called a gradient vector. And so to introduce this and to kind of give you an overview as to what we're going to find, let's consider a function in 3 dimensions. So I'll just draw a 3D axis really quickly. Pretty easy function. So let's do something like this, where we have this sort of function. All right, so maybe it's almost like a sinusoidal function or something like that. And just imagine this function is like maybe a hill or something like that, or a ramp. And let's say we want to pick a specific point on our function. So let's call this function f. And let's say right here. All right, now, and pretend you're like, I don't know, a skateboarder or a skier or something like that, and you're going down the hill. And there's lots of different rates of change in that different direction. So for instance, there's a rate of change this way. All right, so let's say you hit a bump and the bump kind of threw you a little bit to the left or something like that. Or maybe another one just kind of went straight out from there, okay? Or even a third one didn't even hit a bump, you were just going down the same path. Or let's say for some reason you hit a bump and it kind of flung you all the way around, all right? And you wanted to figure out, well, what's the rate of change if I hit a bump and it kind of hit me that way or something like that. And that's what we're trying to find, is we have all these different vectors, all right? So let's say we have a u1 and we have a vector u2 and a vector u3 and a vector u4. And what we're trying to do is we're trying to find the rate of change in the specific direction at that point. Okay, so right here is a point, AB, that exists on our multivariable function. Right? And there's different rates of change. And we probably know that the rate of change of u3 is going to be significantly higher than that of u4, right, if you look at that diagram. And so that's what we're doing, is we're finding these directional derivatives. So that's what a directional derivative is. It's the rate of change, all right? Well, not necessarily the rate of change, but it can model the rate of change in a specific direction of a vector u. Right now, it doesn't have to be a unit vector, okay? Or it does have to be a unit vector, excuse me, otherwise that doesn't make any sense. So if we have a unit vector u, right, then there's 2 different formulas that we can use to find this, all right? So if we know the unit vector, then we could just take the partial of x and multiply it by a, and the partial of y multiply it by b. And remember, the unit vector has magnitude 1, so it's not going to change the magnitude or the scalar of that direction, all right? So we're just going to find the directional derivative and essentially multiply it by a magnitude of 1, which will do nothing. The same thing over here. If we know the angle, we could just use cos and sine of that angle because that represents the unit circle. And we know that any point on the unit circle from the origin has a magnitude of 1 as well. So there's these angular definitions and then there's the vector definition. All right, so let's take a look at a couple examples, all right, and we're just going to start out with our angular definition to make it really easy. So we want to find the directional derivative of the given function f at the point in the direction given of the angle. All right, so first of all, we're going to find the partials. All right, so that shouldn't be too difficult. Nice polynomial. And so for our partials, we're going to end up with f sub x is going to be 2xy cubed plus 8x cubed y. Fy, that's going to be 3x squared y squared plus 2x to the 4th. And what we also would like to do is we'd like to be able to evaluate both of these at a specific point. So that's going to be 1, -2 for both of those. Right, so fx evaluated at the point 1, -2 is going to be equal to 2 times 1 times -2 cubed plus 8 times 1 times -2, and this is 1 cubed, excuse me. Okay. So ultimately that should work into negative 32, I believe, because this will be negative 16 and then another negative 16, so that should be negative 32. And we're going to hold on to that because we also need to figure out what Fy is. Fy at the point 1, negative 2. That's going to be equal to 3 times 1 square times negative 2 square plus 2 times 1 to the 4th. Right? That looks like it's going to end up being 14 because this will be 12 and this will be 2, so we end up with 14. Right? And now finally we're going to find the directional derivative at pi thirds. Right? So we're going to find d sub u of f at 1, negative 2. And that's going to be equal to negative 32 times, and we go back up, it's going to be our cosine since we're in our x direction. All right, so we have fxy cos of theta. So it's going to be cos of pi thirds plus 14 sine of pi thirds. Right? And you probably remember cosine of pi thirds is a half. So this will be negative 16. And then sine of pi thirds is root 3 over 2. Half of 14 is 7. So it'll be 7 roots of 3. Right. So hopefully that's a pretty good introduction to this. Now we're going to take a look at a few more examples of this, both in the directional with the angle, but then also in the idea of taking a look at it with respect to a unit vector.